On my website, there are two video clips, mathematical structures on the space of complex numbers, and another video clip, complex functions. Now we continue by presenting complex differentiable functions. We have already showed that the space of all the complex numbers can be identified to the real two-dimensional space by using this identification. If we identify this complex number with this vector, these two spaces are identical as norm spaces and also as metric spaces. It is just a difference of notation. Now, I shall remind you the definition from high school. A function defined on an open interval AB is differentiable at a point x0 from this interval if there exists and is finite this limit we denote by f prime of x0, limit for x going to x0. Now, if we try to transpose directly this definition to the case of a function of two variables, let D be an open set instead of this interval from this space, then a function defined on D is differentiable at a point of D if there exists and is finite the limit. We can see that this expression is not defined. We cannot divide in this by a vector. In this case, this is a vector. So we cannot extend directly this definition to the case of a function of two variables, but we have this identification, but the possibility to divide by a complex number different from zero allow us to extend the definition you know from school to the case of a function defined on an open set contained in the set of all the complex numbers. We say that such a function is differentiable. We say complex differentiable to specify that in this case we have a special case at a point z0 from the open set D if there exists and is finite this limit. This is just this definition extended to the case when z is a complex number. You know that the space of real numbers, this is a subset of the space, here the space of all the complex numbers. The case of instead of, in this case, our function is defined only on the real axis, a function f defined real values. Now we can take extend this to a function defined on an open set D, differentiable at a point z0. So this the definition you know from school can be directly extended to this to the functions which are defined on the complex plane. So we can directly extend this definition. Let us compute directly a derivative. The derivative, this is called the derivative of our function at point z0. Let us consider as an example the case of a function. Firstly, the real case, f of x equals x cubed. And this case, we intend to compute the derivative of this function at a point x0. By definition, this is the limit for of f of x minus f of x0 over x minus x0 for x going to x0 equals limit x0. Here is x cubed minus x0 cubed over x minus x0 equals limit. This expression, we can decompose it as x minus x0 times x squared plus x0 plus x0 squared over x minus x0. We can simplify here and we get the limit at point x0 will be x0 squared 3 times x0 squared, and this we obtain this for any x0 r. So we have obtained that the derivative of f at an arbitrary point x is 3 times x squared. If instead of f we put directly x cubed, derivative of this is 3 times x squared, a formula you know from school. But exactly this computation can be done in the case of the function, the extension of this function. This is defined on the real axis. Here is the real axis, complex plane, but this can be extended to a function on the whole complex plane, namely the function f of z equals z cubed. And we can, in exactly the similar way, we can obtain that the derivative of this function at a point z0, a point z0, can be obtained in a very similar way. Limit z going to z0. I shall put directly here z cubed minus z0 cubed over z minus z0. We can decompose in the same way, and we get 3 times z0 squared. So the function z cubed, the derivative of this is 3 times z squared, a formula similar which extends this formula from the real analysis. Now let us analyze in more details the definition. In the case of a function defined on the real axis, x tends to x0 only along the real axis, but in the case, in this case, let us, in the real case, if here is x0, then x goes to x0 only on the direction of the real axis. But if we have a point here now, z0 equals x0 plus y0 I, then we can consider, for example, the limit in this definition, the derivative of f at point z0, limit for z going to z0, f of z minus f of z0 over z minus z0. We can consider z tending to z0, particularly along the direction parallel to the axis of coordinates. Let let us assume that this limit exists and is alpha plus beta I. Particularly, let us assume that it exists. Then, particularly, we must have a point here z as the real part is x0 plus y I, and so we must have limit. This point tends to this for y tending to y0. F of z here is x0 plus minus f of x0 plus y0 I over, in this case we have here x0 plus y I minus x0 minus. In this case, and this must be alpha plus beta I. Now let us denote for our function f of x plus the real part. Let us denote the real part of this function by u. And we use this identification. So we consider u as a function of two real variables, x and y, plus I v of x and y, the imaginary part of f. Then this relation becomes limit for y going to y0. Instead of this, we get u of x0 and y. Let us consider firstly only the real part. The real part here is u of x0, y0. This over the y minus y0 I. Now the imaginary part is the imaginary part plus another limit, also for y going to y0. Then this point tends to z0. Limit v of x0 y x0 y minus v of x0 y0 over y minus y0 I, and for v we have also times I, and this is alpha. We denoted this limit alpha plus beta I, but you can remark that here we have let us multiply this relation by I, and then here we have the derivative of u with respect to y at point x0, y0. We have multiplied by I, okay. So plus here is the derivative of v with respect also at point x0, y0 multiplied by I equals alpha I minus beta. We have this relation. Now, in order this limit to exist, the limit along a direction parallel to the real axis, here the point has the form x plus the imaginary part is y0 I, and this point tends to z0 when x tends to x0. So now we have a limit for x going to x0. F along this is f of x plus y0 I minus f of x0 plus over x plus y0 I minus x0 minus. So in this case it remains just this, and this limit must also be the same. The limits along the two considered direction must coincide. We denoted this limit by alpha plus beta I. Now, in a very similar way, here we obtain the derivative of u with respect to x plus this at point x0, y0 plus the derivative of v with respect also to x at point x0, y0 times I equals alpha plus beta I. Now, from these two relations, we get, if we take only the real part, let us consider from, we get derivative of u with respect to x at point x0, y0. This is alpha. And from this relation, if we identify, we can remark that alpha is this coefficient, the imaginary part of this number, is derivative of v with respect to y at the point x0, y0. And now the derivative of u with respect to y at this point, derivative with respect to y at u here, this is the real part, is minus beta, equals from here minus beta is imaginary part, is minus beta is this, so is minus derivative of v with respect to x at points x0, y0. So these two relations are a necessary condition in order this limit to exist. In addition, you can remark that if they are satisfied, they are only necessary conditions, f prime at the point z0 is alpha. Instead of alpha, we can put the derivative of u with respect to x at point x0, y0 plus beta. Beta is from here derivative of v minus minus with respect also to x at point x0, y0 times I. Well, if we assume that this limit exists and has this value, then these are necessary conditions, and in addition, the derivative can be expressed in terms of the derivative of u and v, both with respect to x. Also, we can, by using these equalities, write this expression in a different form. Now, we shall present a fundamental result, the theorem of Cauchy-Riemann. These are called Cauchy-Riemann conditions. Theorem Cauchy-Riemann. Let D from C, which we identified R2, be an open set. Then a function f defined on D, a complex function, which we describe f of x plus y I. We denote by u the real part, which we consider as a function of two real variables. So we characterize the complex differentiability of f by using the differentiability from the real analysis of these functions plus v of x and y I is C differentiable, complex differentiable, at a point z0 equals x0 plus y0 I if and only if the functions u and v from D to R these are real functions, and here we consider D as a subset of the two-dimensional real space, are differentiable at the point x0, y0 is the vector corresponding to this, and in addition, there are satisfied the Cauchy-Riemann relations. These relations are satisfied. In addition, we have a description. If these conditions are satisfied, then we have here a formula for the derivative. Let us use this formula to compute the derivative of some particular functions. As an exercise, let us consider f from C. F of x equals x squared. In this, f of z equals z squared. The real part of this function, x plus yi equals x plus squared, which is x squared minus This is the real part plus 2 times x, y, I. So this is our function u of x and y, and this is our function v of x and y. In this case, you can see that the derivative of u with respect to x is 2x and is exactly the derivative of v with respect to y at any point, and the derivative of u with respect to y is minus 2y, which is minus derivative of v with respect to x. So the Cauchy-Riemann conditions are satisfied, and now uh, these two functions, u and v, are differentiable functions. They are polynomial functions. And as concerned the derivative of f at a point z, an arbitrary point, this will be derivative of u with respect to x plus derivative of v also with respect to xi equals, in our case, derivative of u with respect to x is 2x, and this derivative of v is 2y plus 2 equals 2 times x plus. So we get to z, f of z, to f of z, okay, to z. So we have obtained, if instead of f of z we put directly z squared, derivative of this is 2z, a formula similar which extend this formula extends the formula you know from high school, x squared. The derivative of this is 2x. Now another example. Let us consider the following function and investigate the differentiability at a point by using Cauchy-Riemann theorem. Let us consider the following function: f from c to c, f of z equals z complex conjugate of z. We have to identify the function u and v. In this case, f of x plus will be x plus complex conjugate. So f of x plus is x minus y I. This from this we identify u of x and y is just x, v of x and y is minus y, and in this case derivative of u with respect to x is 1, but it is different from minus 1, which is the derivative of u with respect to y, of v with respect to y, which is minus 1. So we get that f is not differentiable at a point z0, at a point z for any z from C. And a last example, let us consider the exponential function. In the case of the exponential function, f is defined on the whole complex plane. F of z equals exponential of z. In this case, f of x plus is exponential of x plus This is exponential of x times exponential. This is exponential of x times cosine of y plus I exponential of x sine of. This is our function u of x and y, and this is v of x and y. In this case, derivative of u with respect to x at an arbitrary point is with respect to x exponential cosine, which is exactly the same as the derivative of v with respect to, and derivative of u with respect to y is minus exponential sine of y, and this is minus derivative of v with respect to x. So the Cauchy-Riemann conditions are satisfied, and now we compute the derivative at an arbitrary point. So derivative at an arbitrary point, z you know is derivative plus derivative of v also. And in our case is exponential of x cosine of y. This is plus derivative of v with respect to x minus minus. So plus exponential of x sine times I. We put I here before plus I. And so we have exponential of x cosine plus I sine. And you can remark that we have exponential I. That is exponential x plus exponential of z. So instead of f, if we put directly the function, the derivative is itself similar. It extends the formula you know from high school. Now we stop here. Thank you.